Hi, my name is Z, and together with my teammate Wen, we are going to share some learnings about using performance signals to improve video recommendations. We work for the Video Infrastructure org in Meta. Every time we process a video uploaded to our family of apps, or every time our app plays a video on the user's device, we generate information, or what we call signals, that we use to improve the user's experience. Our team applies machine learning to transform such signals into inputs which video recommendations models can use. Hence, we optimize video quality and smoothness, whilst helping users save on resources like device and even battery or memory usage. Today, we will share some ideas and learnings from our experience in using device signals to improve video recommendations. If we take a look at video growth over the years, we see that video is an important part of the user experience, and we want to ensure that the relevant videos that we send to the users can be played and downloaded with great quality. During the pandemic, for example, live video usage increased, with more people staying at home and watching the live shopping or live gaming apps. Short-form video continues to delight users and connect people, and recently, Gen AI video is becoming viral. Because of the diversity of device models and environments where users can enjoy video content, we cannot assume that all videos will play smoothly. To maximize user experience, we need to take into account the video or device performance. Today, we will share three main ideas. The first idea is improving video recommendations with device performance signals. This involves sending signals from the client to the server. We observe improvements in user sessions. The second idea is improving device performance using prediction signals such as predicted watch time. This involves sending signals the other way around from the server to the client. We observe improvements in video watch time and data savings. The last idea is using the same infra, which enables effective, real-time client-server signal sharing to enable personalized video experiences at scale. Now, I'll hand it over to my colleague Wen, who will talk about using bandwidth estimation signals to improve video recommendations.
Thanks, Z. Now I'm going to talk about using bandwidth estimations for video recommendations. In Facebook, real-time bandwidth is constantly measured by looking into the video download speed in the channel between user devices and Meta's multimedia CDNs. This dynamically changing metric could be a key signal to measure network condition and serve as a key factor to fine-tune the ranking model. So we incorporate users' current bandwidth into video recommendations logic to reduce the likelihood of bufferings and lagging. There could be multiple ways to utilize bandwidth signal to fine-tune ranking model in Facebook. For example, in Feed timeline, we can make rules that demote videos that doesn't have low bitrate encoding. Furthermore, we can build machine learning models that utilize videos and network signals to predict negative events like video stalls or blurriness, such that we can counteract by using some primitive measure like down-ranking videos or promoting lighter content, such as text post or photo post. This significantly reduces friction in users' video playback experience. And we already observed sizable engagement wins as a result. Besides bandwidth estimation, some other real-time features are used to measure video playback experience more directly. For example, video stalls happened in previous video playback sessions several seconds ago turn out to be a very valuable signal to guide video recommendations. When users have finished several video sessions, we collect signals like how long users waiting for a video to start and how many times stall happened during that video playback session. This could be due to device memory issue, CPU issue, or network issue. We are using these signals to customize feeds or video chain recommendations. Like introduced for BWE, we either make rule in ranking engine to demote risky videos or build a machine learning model by utilizing these features and maybe video features and network features to predict the risk of similar issues in video playing in next few minutes. We have been actively testing stall signals in several products in Meta. We observed users' quality of experience has been significantly improved in terms of stalls and resolutions. And also engagement and ads avenues have increased too as a result. While ranking can benefit from device signals in the opposite direction, our device video strategies can also be optimized by introducing some signals coming from ranking. For example, watch time signal is a common signal in ranking decision. It will be transmitted to device to guide our video strategy too. Before deep dive into the watch time prediction, there are three key terms that worth mentioning before introducing it. First of all, we have watch time prediction. It defines how much we think this user will watch a particular video. And then we have video prefetching strategy. It defines how many video chunk of the video we should download before users scroll video into the view. We also have device performance. It defines the device metric such as video playback smoothness in terms of video stall and resolution. This diagram introduces how video prefetch works. So first of all, users will open our app and send a video request. Then app receives the response for videos, and it will start prefetching the video chunk. And the viewer will scroll videos into the viewport and start to playing it with those prefetched data. Video prefetch is a key factor impacting users' experience. We have to prefetch the right amount of data for video to deliver the best user experience. If player prefetches less than user watches, the users are prone to experience longer buffering time and even exit the video earlier. In the meanwhile, if player prefetches more than what user watched, it will lead to data wastage, data slaughtering, or network congestion. And as a result, it will still negatively impact users' experience. In Meta, we built deep neural networks to predict users' watch time at user video pair level. We leverage some pre-trained model to generate some embeddings. There are mainly three types of embeddings. First of all, we have video embedding, represents video content understanding results. Second, we have user embedding, which represents users' behavior analysis results. Lastly, we introduce video owners embedding, which represents their friends or followers' average profile. In addition to embeddings, we also add this video's watch time percentiles and users' watch percentiles as additional features. On top of these features, we train a machine learning model to predict users' watch time. We applied the watch time prediction in our prefetch strategy in two ways. In first way, we prefetch less data when predicting user will exit the video in short time. This helped us significantly in reducing users' data wastage. This is particularly important to the cohort of data-constrained users. they end up getting more data to consume content in Facebook platforms, which led to an increase in engagement. In another way, we prefetch more data when predicting user will spend more time in the video. This largely reduced the risk of bufferings and increased likelihood of video deep dive. As a summary, we have a bidirectional signal exchange system in Meta to ensure the mutual beneficial relationship between device strategy and ranking system. Client is sending device health signals to server. Server leverage those signals to optimize video recommendations. Besides bandwidth estimation and stalls, there are more signals that can be potentially helpful. For example, devices' available memory size, salmon state signals, and app crashes signals can all be used to measure the real-time capability of the device and info ranking system. Conversely, server is sending signals like predicted watch time back to the client. And then client can decide the optimal video streaming strategies, such as amount of prefetch size, by leveraging those ranking signals. In addition to predicted watch time, there are more interesting signals to leverage. For example, we have a probability of user will enter the full screen. Also, we have predictions of a users will exit the app very soon. The introduction about the architecture of our signal exchanging system between device and ranking ends here. Now, we'd like to invite Z back to give an introduction about some exciting extensions of it in near future.
Thanks, Wen. Now that we have covered some examples of using client signals to improve server-side models and using server-side signals to improve client performance, let's talk about future opportunities. We dream about the future of personalized video powered by seamless client-server signal sharing. Instead of simple signal sharing, we can leverage on-device machine learning to build embeddings which represent user and device characteristics at that moment. For example, your recent device state like battery level, memory availability, and network condition can be represented by embeddings as a richer signal for server-side recommendation models to deliver the most relevant content that you can enjoy. Also, we can use those embeddings as client prompts for Gen AI. Generative AI can take into account device characteristics when generating content and control for resolution, size, or length of video which the device can actually download and play smoothly. By customizing content based on device capabilities, we can also help users minimize data wastage by serving content that device can actually support, as Wen presented earlier. I hope you enjoyed our sharing about using device signals to improve video recommendations. From Wen and I, thank you, and looking forward to connecting with you.